And let us continue with the presentation. Next up, we have some assembly. Let's start with registers. So these are two different ways to represent these registers that we have. On the left-hand side, you can see that there are bits. We have 64-bit, 32-bit, 16-bit, 8-bit. And on the right side, we have bytes. These are exactly the same thing. These are just different ways to represent them. In this presentation, we won't be focusing on any registers that have numbers on them. So you can see that R8, R9, so on and so forth. We'll be focusing on the other ones above them. And it's good to know how these registers are actually named. So every single 64-bit register starts with the letter R. Every 32-bit register starts with E. Then we have 16 bits, which is just the E removed. And then we have the lower 8 bits, where the X is replaced, usually with just an L. That's pretty much it for the naming. It's also important to understand how the registers actually work. As in, if you look at 64-bit registers, let's take the first one, the A register, RAX. And then to the right of it, you can see EAX. And that EAX register, the size of it is 32 bits, but it's the lower 32 bits of the whole 64-bit register. So we have one 64-bit register, and then the lower 32 bits of that register are just labeled EAX. And then the lower 16 bits of that register are just labeled AX. But it's still within the one 64-bit register. I can actually show you. Alright, let's see. We have our whole 64-bit register right here. 64 bits. Then half of it is 32 bits. Then again, half of that will be the 16-bit register. And half of that will be something else than that. 8 bits. Hopefully that's now a bit easier to understand. And we're back. What are they actually doing? What do they do? Why are they named the way they are named? Well, let's start with the general purpose registers, which is all we are going to look today. We have data registers, which are A, B, C, and D. And you can see the naming protocols. So just replace the multiplication symbol with a letter. In this case, let's take A. So RAX, EAX, AX. Then we technically have AH, which is A and higher 8 bits, and AL, which is the lower 8 bits from the 16-bit register. And same goes with B, C, and D. And they actually have names as well. So A is accumulator, we have B as in base, C counter, D data. But we can use these registers pretty much however we like. It's good to know that mainly every single function returns their value into the A register. That will be important later, but we will look through a demo of that one as well. Next, we have pointer registers. So IP, SP, BP. So those are instruction, stack, and base pointers. One of the more interesting registers of these is the instruction pointer. The instruction pointer always points to the next instruction our CPU is going to run. And that will be very fun later on. Then we have index registers. We have S and D, which are source and destination indexes. We can use these when we copy or compare something to something else. So we compare the source with the destination. Make sense? Then we also have the flags register. And as some of you probably already noticed, it has an R before it, so it's a 64-bit register in this case. And this works a bit differently. We have bits that correspond to different things. Let's see from the top, the first bit, so bit 0, we have a carry flag. The bit number 6 would be 0 flag, and then we have a sign flag, trap flag, and so on and so forth. None of these you are required to know by heart, of course not. You can actually just look every single time you need to. Some of these you probably will just start to remember if you actually do this, but it's nowhere near that important that you should know it by heart. Just know that these exist, and there is a reason for pretty much all of them, especially the carry flag and 0 flag over there. Next up, we have some instructions. From top down, we have mov, which is move to/from memory and registers. So we move data and values from different place to another. Simple. Then we have push and pop, which we use the stack with. We push things onto the stack and we pop them out. Then we have add. We add with carry if we have one. We also have sub, which would be subtract. Add is basically a plus and subtract is minus. Then we have CMP, which is compare. We have the good old bitwise operations. Then we have JMP, which is jump, and this is an unconditional jump. So if you have worked with any kind of programming language really, you can use the go-to statement, and this is basically that, but within assembly. Then we have JE, JNE, JC, so on and so forth. There's also JZ and so on. And these are conditional jumps, so we jump if some kind of condition is met. So JE would be jump if equal. So that means we have compared something, and if those values we have compared beforehand are equal to each other, we take the jump. If it's not, we don't. JNE is jump if not equal. JC would be jump if carry, and that's where the carry flag is. And then we also have JZ, which would be jump if 0 flag is set, and so on and so forth. There are many, many different conditional jumps that we have. And then last but not least, we have NOP, N-O-P, which is no operation. It does literally nothing. And there are many, many more instructions that we have. We will see some others as well later in the demos. But for now, just know that these exist, and it will make much more sense later on. Next, a bit about stack. So, how does stack work? Well, it's LIFO, so last in, first out. The last item you put on the stack is the first item you take away. Think about piling up plates, for example. The last one you put on the top is the first one you take off. Stack grows down in memory, so memory addresses go down as the stack grows. I have an image of that on the next slide, and that hopefully explains it a bit better. But yeah, then we have SP, which is the stack pointer, if you remember. And it always points to the top of the stack. So the last item on the stack pointer will point on that one. And when you add an item, the stack pointer points to a lower address than before, because the stack grows downwards. And here is the image. So let's say we run our program. Some of our RAM, random access memory, gets used by our program, and it contains our stack. It contains the stack, heap, all the data section and text section or code. And on the stack, we actually store our function calls and some automatic variables. Then we have heap. We won't really go into too much detail today at all, really. But it's for dynamic memory allocation. Then we have data, which includes initialized and uninitialized data. And then we have our instructions or text, and that includes basically our code. Yeah, Next up, let's look a bit of the disassembly tools we have. We have GBD, which runs on Linux, Unix systems in general, Windows and Mac OS X as well. It doesn't cost anything, it's free of charge. And basically comes with, I can't really say all, perhaps, but at least all of the most popular Linux distributions, it's built in basically. And then we have OllyDBG, Olly Debugger. Runs on Windows systems, doesn't cost anything. Really good, I've used it before. Fairly simple to work with. Then we have Radar 2. Runs on Linux, every kind of BSD, Windows, OS X, Android, iOS, Haiku, Solaris, and many more. It probably runs on everything I know. It doesn't cost anything, it's completely free, and it supports at least 60 different CPU architectures as well. And this is the one I've been using the most, and I will be also using this one on the demos coming up. Then we have Binary Ninja. It runs on Linux, Mac, and Windows, officially supports 8 CPU architectures, unofficially a bit more, I think like 12 or 13, I believe. I don't have the price here, but it's like, I believe it was like $120 for a year or something along those lines. It's not that expensive. It has a nice graphical user interface as well as a decompiler, which tries to decompile the disassembly code back into C code. Then we have IDA Pro, which is Interactive Disassembler Pro. Runs on Linux, Windows, ARM, macOS. This is the industry standard. It supports over 50 processor architectures, but it's fairly expensive. It's about 2,000 euros per year, per user as well. But this is the big boy weapon, so to speak. Or at least was. I believe still is as well. Because now we also have Ghidra, which runs on Linux, Windows, Mac, 64-bit. It's free, it's open source. It originally was leaked in, I believe, Vault 7 or 9. It's one of the NSA tools, the tools that NSA uses, that was leaked back multiple years ago. But after that, NSA decided, okay, well, it has already leaked, so what should we do with it? Well, they opened it up, so it's now an open source tool that is developed by NSA, and it's really good. I highly suggest at least trying it. But yeah, then we have the demos. Let's go into that one.